You can see it?
Yep.
Oh, okay, great. Sorry, I couldn't hear you. Great. Well, good evening, everyone. Thanks so much for the invitation to speak today. Um, as you heard, my name is Anna Ho, and I'm currently an assistant professor in Cornell's astronomy department. I wish I could have been there in person. Unfortunately, just couldn't leave Ithaca in time to drive over this evening, but I really hope that I can come back and meet you all in person sometime in the future. Maybe by then T-Core Bohr will have gone off and I'll have we can chat more about that. I also just wanted to mention that yesterday I was on a Zoom call and my laptop abruptly shut itself off and rebooted. I hope that doesn't happen again. It seems fine today, but if I disappear, then I'll just be back in a few minutes. Okay, so with that aside, I do research on the lives and deaths of stars, as well as on the afterlives of their corpses or their remnants. For this research, I use telescopes located in deserts and on mountaintops all over the Earth, as well as on satellites in low Earth orbit. And I try to study how a star's properties in its life determine the manner of its death and the type of corpse that it forms. So whether, for example, that corpse is a neutron star or a millisecond magnetar or a black hole. And a unifying theme in my research is the observation and interpretation of change. So the signals that I collect from the stars and their corpses change quickly on timescales that we can perceive, and most of them cannot be seen by the human eye. And so tonight I'm going to give you an introduction to that work. And I hope that this can be, sort of a conversation. So please feel free to ask me questions afterwards. Or if you're online, you want to interrupt me during the talk, I'm also totally fine with that too. If we don't get to your question today, also feel free to send me an email, and I'd be happy to be a resource for you. Okay, so before I launch into stellar death, I thought I would sort of try to orient you by talking about what the night sky looks like to our eyes, which I know many of you are already familiar with, but just to get everyone onto the same page. We know that the human eye is an incredibly powerful detector. We can distinguish between a huge range of colors. We can see a huge range of brightness. So the faintest light we can see is a factor of about 10 billion fainter than the brightest light we can see. And our eye takes a picture and sends the picture to our brain about 15 times per second. And this rapid frame rate or imaging rate enables us to notice very fast changes in our surroundings and to react quickly. Now, when you use this detector to look at a dark sky, as you all know, you see something like this. So, of course, pretty much every single dot here is a star inside our galaxy, the Milky Way. If it's very dark, you see this band of fuzzy white material. That's basically just a lot of stars. And in some areas, these stars are blocked by what look like dark clouds. And these are clouds in a way, but they're actually clouds of gas and dust that lie between the stars in our galaxy. Now, there are only a few objects outside the Milky Way that we can see with our eyes. The Andromeda Galaxy, which is the closest big galaxy to our own, and the LMC and the SMC, Small Magellanic Cloud, Large Magellanic Cloud, which are small satellite galaxies orbiting the Milky Way. And if you look at the sky every night, you'll notice some changes. Of course, the position of the moon and the planets might change, and you'll see a shooting star, meteor, comet. And if you're very lucky, approximately once every century, you'll see something very dramatic. So this is a picture of the Milky Way's larger satellite galaxy before this particular day in 1987 and shortly afterwards. And so I don't know if you can spot the change in this image, but there's actually a new star at that location after this day, visible to the naked eye, although these particular images were taken with a camera. So if we take a closer look at that location using a telescope, which offers several major improvements, it's bigger, so it collects more light, can see things that are fainter, has much better resolution, so you can see individual stars and what looks like otherwise a blur to our eyes. So here's an image from a telescope of that position before on the left. There's a star here, a type of star called a blue supergiant, which basically means that as far as stars go, it's quite advanced in its age. And afterwards, that star was confirmed to have disappeared. And in its place was something 200 million times brighter, which, as you can probably guess, was a supernova. And so this supernova 1987A is by far the best studied supernova ever because it happened so close to Earth at a time when we had telescopes to study it. We learned a lot about stellar life and death from this event. And so it's a very useful introduction to this topic. And so I'll now just tell you a bit more about it before I go into sort of modern supernova research. Okay, so first, just a very brief overview of this topic. Our understanding is that stars form when a cloud of gas and dust collapses and heats up. If the star is similar to the sun in terms of how much it weighs, it lives for billions of years before becoming a red giant. This star shines by burning fuel in its core, but eventually it runs out of fuel to burn, and the outer parts of the star kind of blow off, become a planetary nebula, and the inner part, the core, is exposed, and that exposed core is called a white dwarf, which is usually made of carbon and oxygen. If, on the other hand, the star is very massive, so it weighs more than around 8 to 10 times the mass of the sun, it goes through its life much more quickly. So whereas a star like the sun lives for billions of years, what we call a massive star only lives for millions of years before it becomes a red supergiant. When this runs out of fuel to burn, it explodes as a supernova and forms a neutron star. And if the neutron star is massive enough, this is about as massive as matter can get. So it becomes more massive than that. It collapses and forms what we call a black hole. Supernovae are really remarkable celestial events. In the first 10 seconds following the collapse, a region about 20 miles across radiates more energy in that 10 seconds than all the stars and galaxies in the rest of the visible universe combined. And this might sound kind of scary, but it's actually quite wonderful because these events are the origin, as we heard earlier in the meeting this evening, of the elements that we need for life, carbon and iron and oxygen, nitrogen, and others. So these elements are not made during the explosion, they're made inside the star, and then they're sort of shared with the universe during the supernova. There are some elements that are actually made during the explosion itself, because matter gets heated to some high temperatures. So it's sort of a combination. Okay, so that's what I would describe as the textbook story of stellar life and death. It's what we teach students in an introductory astronomy class. And supernova 1987A was an amazing vindication of many aspects of this textbook story, but it also brought some big surprises. So first of all, this was the first time astronomers actually saw the star before it exploded, which confirmed that stars do explode and that supernovae are really dying stars. But it was the wrong type of star. Astronomers expected a red supergiant, and this was a blue supergiant. And so this forced a revision of the textbook story of stellar life and death, one that requires taking into account the composition of the gas that the star is made of. And today we know that that's an essential part of the story. And just to tell you a little bit more about the star, astronomers think it was around 18 times the mass of the sun and that it lived for around 10 million years. And actually something I'll mention now, but then return to later, is that it spent almost all of those 10 million years burning through its hydrogen, and then just a million years to burn through its helium, about 12,000 years to finish its carbon, 12 years, just 12 years to do its neon, 4 years to do its oxygen, and we think just about a week to burn through all its silicon and reach iron. So these final stages happen very, very quickly. And that's important, and I'll say why later. Okay, another major landmark in supernova 1987A was the detection of these mysterious particles called neutrinos. Neutrinos are tiny particles. You've probably heard of an electron, a tiny electrically charged particle. Neutrinos are called neutrinos because they're neutral. They have no electric charge. They're way tinier than even electrons. Because they have very little mass and no charge, it's really hard to get them to interact with anything. The Earth is much more transparent to neutrinos than a sheet of glass is to light. But there are dedicated experiments under the Earth that can detect neutrinos. basically by constructing a giant tank of water and detecting the tiny signal from a neutrino interacting with a proton in the water. Until this point, until this 1987A, neutrinos had only ever been detected from the sun.
Yep.
But they were predicted to be the very first signal to leave a supernova, and indeed, they were the first signal detected from 1987A. And 3 different detectors detected those neutrinos washing over the Earth. Amazingly, the amount of energy contained in these neutrinos was exactly the amount of energy that you expect a star to release when it collapses and forms a neutron star, with exactly the predicted mass of the neutron star and the predicted temperature. So that was an amazing vindication of the theory that stars collapse and form neutron stars. I gave a talk sort of like this pretty much exactly 1 year ago, February 2024. And when I gave that talk, I said on this slide that a big open puzzle is that we have not seen the neutron star, and people are still looking for the neutron star. And if the neutron star is found, it'll be huge news. But this year, I get to tell you that there now is strong evidence from the neutron star from the James Webb Space Telescope, from a spectrum, which took 37 years. Basically, the reason is that for a long time, the thing has there's all this debris around, and you don't see. It's sort of hard to see into the heart of the explosion. But at this point, decades later, it seems like we are the material is becoming transparent enough for us to actually see it. And so this is a sort of map of the area, and those little contours are showing where this new source is coming from. On the right, it's basically a spectrum of that source at the center. It's a highly ionized species of argon, and it's just very, very hard to imagine getting this from anything other than a neutron star. So that's actually very, very exciting. Just came out last year. Okay, astronomers also got amazing spectroscopic observations of supernova 1987A. This is a spectrum in the infrared part of the electromagnetic spectrum. Different elements give rise to different peaks or different features in the spectrum, and you can read a spectrum like a fingerprint to identify which elements are involved. And again, this was a sort of spectacular demonstration of the abundances of different elements that are produced in stars and in supernovae. And there's just one more thing I want to mention about supernova 1987A, and that is that its structure was extremely complex. So this is an image taken with the Hubble Space Telescope. The source has 2 rings, one kind of stacked on top of the other. And over time, astronomers have been able to watch these rings change. So this is a time-lapse footage over the years showing the rings brightening. And what probably happened was that the ring actually formed about 30,000 years before the star exploded. So it's kind of a fossil record of the final stages of the star's existence. And then the light from the supernova, or the kind of debris ejected from the supernova, crashed into the ring and heated up this gas, this pre-existing gas, which caused it to light up. So you might ask, why would a star have a ring surrounding it when it exploded? This teaches us that stars do very complicated things shortly prior to their deaths. And today, we actually understand that these sort of death omens are one of the most important predictors of how the star will die and what type of remnant it will leave behind. I'll say more about that in a minute. Okay, so just to summarize here, this is what's called a light curve of supernova 1987A. A light curve shows brightness over time. And so the x-axis here, the horizontal axis, is in days. So there's the time of explosion on the left, 100 days later, 200 days later, 300 days later. The y-axis shows the brightness or the luminosity in units of the brightness of the sun. So at the moment of the explosion, there was this burst of neutrinos that I told you about. Then it faded away. And then it brightened over the course of a couple of months and then faded away again. And this kind of time scale is pretty typical. Most supernovae brighten over a couple of months and then they fade away. And at the peak, they are actually more luminous than the rest of the galaxy that they occur in. So they outshine the rest of their home galaxy. So 200 million times in this case, the brightness of the sun. Okay, so we learned a lot, as I said, from supernova 1987A. Just to recap, we detected the star, we found neutrinos from a supernova, we now have evidence of neutron star formation, showed that elements are synthesized, they have very complex structures, do things before the explosion. And this was a hint that our textbook story of stellar life and death is not complete. And today, what we're really doing is trying to kind of rewrite that story to take into account all these really poorly understood aspects. And so now I'll talk about how we actually discover supernovae today. Today it's very, very different. We are not just waiting for once a century to find a nearby supernova. This field today we actually most telescopes that are discovering supernovae are equipped with much more sophisticated detectors. Usually sort of big CCDs, now starting to be CMOS detectors as well. Telescopes are fully roboticized to scan the sky and look for new kinds of supernovae. And at this point, we find a new supernova pretty much every night. So the rate has completely changed. This is a picture of the telescope that I do a lot of my research with. It's called the Zwicky Transient Facility, and it's based at Palomar Observatory in Southern California, kind of a couple hours from San Diego, or near Temecula, if you have heard of that. So this picture is inside the barrel of the telescope, and this is a giant CCD camera that was mounted to fill the focal plane of the telescope in 2018. This telescope, when it was first built, construction ended in 1948. And it spent about a decade making a map of the entire night sky visible from Palomar. But today, the same telescope is fully roboticized. It has this big focal plane filling CCD camera, and it can make a map of the entire sky within just a single night. So the technology has really driven this field and completely changed what is scientifically possible. This is 1/64th of a real ZTF image in a negative. The full field of view is about 47 square degrees, and you can sort of estimate how much that is. So say it's something like 7 by 7, so that's a couple of your fingers extended out at arm's length, which maybe doesn't sound like a lot, but at least as far as survey telescopes go, it's basically the biggest one around, which is basically why it's able to map the whole sky so quickly. DTF is just one of a number of surveys. Basically, every single night, our night sky is being robotically mapped by a whole suite of telescopes all over the Earth, and they find new supernovae fully autonomously. So the way this works, this is kind of a zoom in of that previous image. ZTF or another facility will take an image, they'll subtract what's called a reference image. So that's an image of what the sky kind of normally looks like at that location. And then every significant change results in what we call an alert. And an alert it's sort of like a little packet of software that just says, this is what we saw, this is where it was, here are some of its basic properties. It's a whole thing I could say about it. I won't get into this too much. The system that we use to distribute these alert messages to allow downstream listeners to actually, go through the alert stream, even to rewind if they need to. You also want to make sure it's very secure, that you're not going to lose data if the connection drops. You need to preserve the integrity of the data and the data format. And so we're actually using the same system that is used by LinkedIn for activity stream data, and is also used by companies like Twitter and Netflix. So this is really kind of an industrial scale process at this point. And so the main message, that's what I meant to show here. This is what the system's called, Apache Kafka. So the main message here is that a new supernova really isn't particularly surprising at all anymore. And from that, we really have a census of supernovae in the universe. We know the different types of supernovae and their relative rates. So just to give you a sense for the sort of data volume here, on a typical night, ZTF will generate a few terabytes of data. So last night, for example, it generated about 200,000 of these alerts. Of those, I'd estimate that about 170,000 are sort of unique sources. You can sort of group them by spatial position. I'd say about 100,000 of these are kind of real. We have a lot of things that are subtraction artifacts. Of those, you have to go in and sort of require that a given source have two or more detections separated by about 30 minutes, because otherwise many of the sources that you get are actually asteroids. So they're things that are streaking across your image. They're not stationary. And so the way that you remove that is you require a source to stay at the same position over about 30 minutes, and that does the trick. So zooming in on that, at that point, most of the things you're left with is activity from stars that are located inside the Milky Way. But what we're actually trying to do is look out through the Milky Way at supernovae happening in other galaxies. And so you have to try to remove as many of those stars as possible. And I did something very basic here and ended up with about 3,000 candidate extragalactic sources, so candidate supernovae. And then of those, only about one of those sources was actually new, so detected for the first time that night. And in my own work, I typically focus on those new sources because I'm looking for things that are very recent post-explosion. All right, so this is an animation that actually is slightly, I just realized I should update this because this was made, I think, about a year ago. But in any case, this is just an animation showing the number of supernovae discovered and then also classified into type of supernova by ZTF. So you can see we don't discover supernovae in the galactic plane. That's because it's very dense, and so it's very hard to see through it. There's just so much extinction. There's also this gap here, which is because ZTF can't see through the Earth. And these are color-coded by supernova type. So most common by number, supernovae are these exploding white dwarfs, thermonuclear supernovae called type 1a supernovae. The blue dots are collapsing massive stars. That's the type of supernovae that I've been talking about. And then there are all kinds of other sort of exotic supernovae whose origins are not really known. And the example being shown here is something called superluminous supernovae that I don't really have time to talk about. Okay, let's see. How do I go to the next slide here? Great. Okay. So with all these supernovae, it's actually still very, very rare to have a supernova that's close by enough that you have an image of the galaxy from beforehand, say with the Hubble Space Telescope, that tells you what type of star actually exploded. So at this point, even though we have 10,000, we have actually recently gone past the marker of classifying 10,000 supernovae. Only 17 supernovae had pre-explosion detections of the star. And actually, from some of these, it's now been confirmed that red supergiants do indeed make core collapse supernovae. All right, so that's sort of an update on how supernovae are discovered today. I'll just tell you a bit about how their corpses are studied today, starting with neutron stars. So just to remind you, we sort of think that whether you get a black hole or a neutron star depends basically on the mass of the star. So stars greater than around 20 times the mass of the sun end up as black holes. Stars less than around 20 times the mass of the sun end up as neutron stars. And so just zooming into these, so neutron stars are typically the size of a city like Manhattan, but they are very dense. So you have something that weighs about as much as the sun, but it's the size of a pretty small city. And so they are extremely exotic events and are used to test sort of fundamental theories of physics that are very difficult to test in a laboratory on the Earth. About 3,000 of them are known, and the vast majority of them have been discovered as what are called pulsars. Pulsars were initially discovered about 60 years ago now by Jocelyn Bell Burnell in Cambridge University. For her thesis work, she strung up miles and miles and miles of cable that basically acted as antennas. So I heard you talking about a radio telescope. This is another type of radio telescope. And when she got her data and looked at the chart paper, which is how it was recorded at the time, she saw these quite regular pulses and figured out that these must be coming from elsewhere in the universe. They could not be terrestrial. And today we know a lot more about these so-called pulsars. A famous one is called the Crab pulsar. It's supposedly in this cave painting. The supernova itself was seen from the Earth in 1054 CE. And this is I guess, actually, I used to tell people this is recent. This is now over 10 years ago, amazingly. This is with a really fancy high-speed photometer at the 200-inch telescope at Palomar Observatory. This is the one, the Corning glass made this incredible, enormous mirror that was the biggest telescope in the world for 50 years. And this is imaging of the Crab pulsar supernova, sorry, the Crab supernova remnant. So there's the remnant, and you can see at the sort of heart of the remnant something pulsing. That's actually the pulsar. So that is the neutron star left over from the supernova. It's just amazing. It's an optical image. It's really quite amazing. So you can see these pulses actually in radio and optical and X-ray, sometimes even in gamma rays. And this is sort of the model, artist's impression. You have these magnetic field lines, you have these beams that come out from the North and the South Pole. And then as this thing whips around, you get a lighthouse effect where sometimes the beam flashes by Earth, and then you see the pulse. That's where the sort of pulsar behavior is thought to come from. And I have very warm feelings about pulsars because this was actually the subject of my very first research project in astronomy. So that's me in college. I got to go to the Green Bank telescope, which I used to discover a pulsar. And I got to go up to the dish and actually touch the dish. Radio astronomy, I love radio astronomy because the wavelengths are so long that the telescopes are much more robust than optical telescopes. So the distortions you're allowed to have on your surface is basically related to the wavelength. And since these wavelengths are long, radio telescopes, you can even walk on the dish. That's allowed. You'd never be allowed to do that for an optical telescope. And I've always loved the sort of accessibility of these facilities. Okay, so just to say a little bit about black holes, right? So this is the neutron stars are as dense as it gets. If you get any denser, you collapse and form a black hole. These are very exotic objects. You've probably heard that they're called this because nothing can escape, even light, that these don't emit or reflect light. But something that I want to mention that I think is not always appreciated is that these are, even though they themselves cannot, light cannot escape what's called the event horizon of the black hole, but they have such powerful gravitational force that they are actually the engines of the brightest events in the universe. So their immense gravitational energy can basically be converted into light. And this happens outside their event horizon. So it's not breaking, the rules here, but the brightest photon sources we know of in the universe come actually from just outside the horizons of black holes. So they're actually responsible for very, very bright things, even though they themselves cannot have light escape their event horizon. This is an example of that. So this is what's called an X-ray binary. This is something in the Milky Way. So basically what happens is you have this black hole. It has a companion star. The gravitational pull is so strong that it sucks in the gas from the star. And then all this material experiences friction and it heats up, and you end up basically shooting these jets out. And if you are really placed in the beam, these can appear extremely bright. Another major development in our understanding of black holes has come from gravitational waves. So you've probably heard about this discovery in 2017 of the first gravitational wave detection from a black hole merger. So gravitational waves are essentially just a different way to perceive the universe. It's not sight, it's not sound. It really is measuring the stretch and shrink of matter on the Earth, and measuring that to an unbelievable level of precision, like at the subatomic precision. It's really an incredible technical feat that this has even been possible. And a lot of the theoretical work for this has been done at Cornell, and then much of the experimental work. There's a big center of this in Syracuse, at Syracuse University. So if you are looking for speakers, I definitely recommend reaching out to some of the folks there because they're doing really exciting, cutting edge technical work on building gravitational wave detectors. So what happens, it turns out quite frequently in the universe, is you have two black holes. Maybe you had two stars that were going around each other. One went supernova, made a black hole, and the other one went supernova, made a black hole, and they were still bound to one another. And then eventually they, fell into each other's gravitational influence and then merged to make a bigger black hole. And when they do that, the sort of asymmetry, the kind of asymmetry of the system produces these ripples of space and time that we can detect now very routinely from the Earth. And the folks in Syracuse and elsewhere, they're now planning a sort of next generation gravitational wave facility that, if it's built, it would actually be able to detect, I think, all of the merging black holes in the entire visible universe. And that would be really, it's kind of pretty mind-boggling. Okay, so in the just the last few minutes here, I want to say a few words about what I've been working on most recently. Once you start discovering a lot of supernovae, you start finding ones that really don't behave as expected. And there are reasons to focus on those because we often make enormous progress in our understanding from finding the cases that kind of break our models, because often they expose, our ignorance about important parts of these models. And so odd cases can actually help us make significant progress in understanding even widespread behavior. So I'll just show you one way to think about this. And this is a diagram that's very commonly used in the study of supernovae. You put the duration of the how long the sort of signal from the supernova lasts. So remember, if you think back to 1987A, I mentioned it gets brighter over a month, it fades again over a couple months. So that's very typical. And then the peak brightness is something like the Milky Way brightness, so the brightness of the Milky Way galaxy. And so on a diagram like this, you can put the normal supernovae basically on the bottom right. 1987A would be located on the bottom right. And there's actually a line that demarcates where supernovae are allowed to be based on our understanding of the physics of how their emission is being produced. And what's happened in the last few years, what I've been working on is really investigating the not allowed part of parameter space. So now I've put in actual data points on the bottom right, the sort of two most common types of supernovae. And my collaborators and I have been discovering all kinds of phenomena that really shouldn't be allowed if they were actually supernovae, which means that something else is going on. These have all these funny names: orphan afterglows, LF bots, blah, blah, blah. And I'm not going to really explain what exactly those are. I don't really have time. But I just want to just give you a glimpse that there's actually a lot going on much faster timescales. And actually last year, or let's see, 2 years ago now, I guess basically a year and a half ago, we actually discovered some events that were supernova-like in their brightness, but only lasted a few minutes. And we really don't know what's going on there. Okay, so which is some of these events? Why are they interesting? What are we learning? Without getting into too much of the weeds of it, one of the most important things that we've learned is that it's actually very common for stars to explode surrounded by very dense gas. So I mentioned that supernova 1987A had this kind of ring when it exploded, and we've realized that that's actually fairly common. And why is that common? How is it that the star, so sorry, just to clarify, if you have a ring around you at the time you explode, it means that after living for millions of years, for some reason, in the final day or the final week or the final month or maybe the final century, so a very, very short fraction of your life, you ejected that ring. And so the question is, how would you know to time that? How would you know that your explosion is imminent and then shed a significant fraction of your atmosphere? And this goes back to what I said before about the final stages of stellar evolution actually being quite fast. So the first stage, the burning the helium in your core, that's what takes 10 million years. But by the time you're burning your silicon, that only takes a day. And so the thinking is that as you progress in these different stages of stellar evolution, the luminosity, the brightnesses, the energies the temperatures get orders of magnitude higher from step to step to step. And so by the time you're in these last phases, things become very, very unstable. And we think that the star is actually becomes sort of unstable to the extent that it actually loses a bunch of its material. And if that's true, then that's actually really exciting because, first of all, it means that potentially we could even learn to predict when a star is going to explode. And it also means that even though all this business of burning elements happens inside the core of the star, that information can be communicated from the core of the star to the surface because it's at the surface where you're actually losing material. And so that would mean that there actually has to be a form of energy transport inside stars that we didn't know existed. So sort of a new way to transport energy in stellar interiors. Okay, maybe I'll skip this just in the interest of time, and I'll just mention one very last mystery. So I mentioned that we've been finding some of these really strange minutes-long events. And this happened when let's see, how do I even phrase this? Okay, so in 2018, there was this survey, kind of like ZTF, that found this supernova-like event. It was called AT 2018 COW. The reason it was called this is that when you find a new supernova candidate, you just name it astronomical transient, the year of discovery, which is 2018, and then a string of letters corresponding to the order in which it was discovered. So it'll be A, B, C, A, B, A, C, A, B, A, C, and so on. So it was by total coincidence, this was 18 cow, and so everyone started calling it the cow. And nobody knows what this was. My collaborators and I have since discovered 10 more very similar things. We've gotten amazing data, but we still don't know what they are. So maybe some kind of weird supernova. It might be a merger of a star and a black hole. Um, so this is a mystery in and of itself. And then this is a series of 5 images that we obtained 100 days after one of these supernova-like events, so events similar to the cow. And so what you're seeing here, so these images each were a 3-minute long exposure. So this is a 15-minute sequence from end to end. And at the position of the crosshairs, so there's this little smudge, which is the galaxy that this event happened in. And the position of the crosshairs is the position we were looking at because that's where this event, this sort of supernova-like event happened. And if you see, there's kind of nothing in the first image or the last image, but there's clearly something in the second image and the third image, and then it fades away again. So that's this minutes duration event that I was telling you about. So something got actually as bright as a supernova within minutes, but in the aftermath, 100 days after another supernova, and then disappeared again. The only explanation we've been able to come up with is that this is the activity of the newborn black hole, perhaps. Maybe it launched some kind of outflow, but it truly was shocking, and I think is actually the most surprised I've ever been in my professional, in my career. It's always exciting to see things that you just absolutely were not expecting to see. Okay, so I'll leave it there. I want to make sure people have time to ask questions. So I'll just summarize and say that the night sky is a very dynamic place. We've had a textbook story for a long time about stellar life and death, but today in this sort of modern era of supernova discovery and gravitational waves and our ability to better study pulsars and black holes, we are basically rewriting that story by taking into account effects that were not appreciated before. The fact that stars seem to know when they're going to die, that actually most stars are in systems with other stars, which actually really significantly influences their lives. Understanding how the composition of the gas and the rotation of the star comes into play. And I've left my email address here, and you're very welcome to reach out if you have questions. So maybe I'll just end there and take any questions that you have.
Just curious, are there stars and galaxies in the dark universe?
Are there stars and galaxies that are, sorry, you're a bit quiet.
That are part of dark energy in the dark universe.
That are dark energy?
Only 10% of the universe is visible.
Right.
90% is dark energy.
Right.
Is dark energy form some form of stars or galaxies?
Oh, I see. So sort of what is dark energy, I guess is the right. So, okay. So yes. So it's true that in terms of, by energy, a very small fraction of the universe is in visible matter, luminous matter, things like that we're familiar with. Then so let's say just roughly something like 10%. then maybe another 20% is dark matter. So this is matter in the sense that it behaves gravitationally. So it has a gravitational force that is related to presumably how much mass there is of that substance, whatever it is. Probably it's some kind of particle that we just don't know about yet, but the nature of that particle is not known. And then the vast majority, say 70%, is actually this dark energy, but that does not behave like matter. So it has no gravitational. You can't weigh it. It's not something that the more there is, things orbit around it, and you can estimate the mass of whatever is there, like you can with dark matter. So it's not something where you would say, it's like a star. But we can detect its influence on the universe. It has caused the expansion rate of the universe to accelerate. So it acts more like it's sort of let's see how best to describe it. You can sort of mathematically describe it as if you imagine having nothing in the universe, you take all the matter out and you just have the universe there, you would still have this. Yes, okay, I can't think of a way to describe it without using all this, sort of vacuum energy. And so it's basically just an underlying energy in the universe that is always there, even if you were to take all the matter out of it. And the bigger the universe is, the more of it there is because there's more space in the universe. So there's sort of a fixed amount of it per space. So as the universe expands, there's more of it, so it expands more and it expands more. But you can't really think about it as an object like a star.
For you had the graph that showed the extreme supernovas and let's call it classical supernovas.
Right.
Were in the lower right of the graph. It's not the same phenomena, but how would a kilonova compare to the energies of the other exotic objects that you had on that graph?
Oh yeah, that's a very good question. And actually, one of the objects there was a kilonova, but I just didn't mention it, so I can show you exactly where that is. Let me just pull up that particular slide. Okay, sorry, this is the graph that I had. AT 2017 GFO is a kilonova, very famous. The kilonova associated with the merger of two neutron stars that were detected via gravitational waves. So it's quite a different thing from conventional supernova.
That got detected by gravitational waves and then over a period of time by various other wavelengths.
Yes, exactly. It was discovered. So first, let's see, which one actually was
gamma ray?
Yeah, it would have been right. So there was a gamma ray burst, there was a gravitational wave, but it had to be the gravitational waves first because that's from the in spiral. Then it merges. Then you get the gravitational waves. Then you get the kilonova that observed with optical telescopes, infrared telescopes. The jet was measured with radio telescopes, X-ray telescopes. Probably the best observed cosmic event ever.
I think one other question then regarding the 1987A
right
supernova, and you said that was first detected by neutrinos,
right?
And you showed the locations of 3 detectors,
right?
Were they able to localize based on the neutrinos where in the sky that was, or did that come later when they could visibly observe it?
Yeah, that's a very good question. My understanding is that neutrino detectors, yeah, that's a very good question. I mean, so I'm a little more familiar with the ones today and what they're capable of in terms of their localization. But I agree with what you're saying, which is if you have multiple of them, you'd think there'd be delays between them that would tell you kind of where it's coming from. But I actually don't know with those specific facilities. And the delay, I actually don't know what precision they could get on where it was coming from. I also don't know if they noticed in real time. So I don't know if they were doing kind of real time searches like that, or whether it's that the supernova was sort of seen and then they realized that they had detected the neutrinos. I'm actually not sure.
Yeah, this is Michael Richmond. I'm an astronomer here at RIT, and I'm
Mhm.
really enjoying your talk, learning a lot about the stuff you're explaining. I happen to teach a course that talks
Oh,
about
great.
sections of supernovae, and I was around for 1987.
Oh, great.
Um,
Okay, so yeah, you can answer better than I can.
the answers are, it was first noticed by a person working at Ceratololo, who
Okay,
looked up in the sky with his naked eye and said, huh, there's something in the LMC that usually isn't there.
right,
Then a bunch of people looked all over the place, including the neutrino people,
right. Okay,
the detectors. 2 of the 12 neutrinos detected at Brookhaven came from the right direction.
okay,
10 of them didn't.
okay,
People who know about it can explain why.
okay. Okay, that's very helpful. Thank you.
I have a question for you.
Sure.
You're doing a lot of work with looking at the new transits that come in. Do you ever get any information from the group in Japan using the Tomoe Gozen wide field camera, who are also looking for transients that may only last a few minutes or a few hours?
Yeah, no, that's a very exciting, definitely a very, very exciting experiment. I've seen talks by them. I'm not really working directly with them. Um, but yeah, it's definitely an exciting experiment. I'm working closely with others who have some similar sorts of facilities trying to do very, very high cadence observations. As far as I know, the sort of latest I've heard um, is that none of these experiments have yet blindly found a really fast extragalactic optical transient. We've just found this one from following up previously known transient, but they certainly should at some point, and I'm excited to see. I'll be really excited when that happens. But yeah, I'm not working directly with them.
Well, Douglas, I read about a few of these stars that just vanished. Have you studied any of those?
Right. So there are, so yeah, I guess depending on what exactly you're referring to, there are now a few cases where, so, okay, so I guess one of the big open questions is what fraction of stars actually make supernovae? Because one, it's actually thought that many of them might just collapse directly and form black holes and not actually explode at all. But that's very hard to find because the supernovae are so bright that it makes them much easier to see. And so one strategy that people take is to monitor known stars and then wait and see, look for the ones that have disappeared. And if you monitor enough, you would think that at some point you'd see the disappearing ones. So people have found a couple that have disappeared. The difficulty is in interpreting what it is that you've seen, because just because it's gone so typically you're monitoring it with an optical telescope. Just because it's gone in the optical doesn't mean it's really gone. It could mean that it's just ejected some stuff and now it's very dusty. And so it's blocked in the optical. But then if you look in the infrared, you actually can see it there. So one of the famous candidates actually, I think there was a JWST observation and they see it. And so they argue that you can't really, it's not so clear that this is actually really gone. I mean, I think it's a little, it could be something else. I think it's fainter still, but it's not gone. And so what exactly are you seeing? So my understanding, from talking to folks who work on this is that, there are these candidates, but it's just very hard to really prove in any of these cases that that's actually what happened, that it was actually a star that's gone and is now a black hole. And there are actually some people who work in this area that there's no such thing, that you actually don't expect. If a star just collapsed and formed a black hole, that it's actually not true that you would see nothing, that you actually should make some kind of bright event, not a supernova, but something that just comes from the fact that you'll still have some sort of release of energy that sort of has to get out somehow. And so it's sort of unavoidable that you'll get some kind of bright transient event. So I think it's still a bit, my impression is that people just are still kind of debating this.
So I was wondering about the fast optical transients and whether any of them have had associated detections in other mediums like neutrinos or gravitational waves, or have they all been optical detections only?
Right. So the fast, I guess just by Right. So the things that I was showing on this graph as fast optical transients are all things that were discovered by optical telescopes, just sort of by definition. But there are certainly many fast optical events that are discovered by first finding, for example, a gamma ray burst, and then you follow it up with your optical telescope, and then you see a very fast optical transient. That's a very routine thing. What I have been working on, I guess what's a more recent development, is that we can actually find these things blindly with optical telescopes because optical telescopes have gotten so much more powerful than they used to be. So of the ones that are found with optical telescopes, many of them have been studied in great detail all across the electromagnetic spectrum. So we get X-rays, radio observations, and so on. None of them have a neutrino detection. There's actually, well, okay, there is one case of a fairly fast optical transient that had a coincident neutrino. The problem is that with this business, it's very hard to prove an association because there's always, just for a single event, there's always kind of an appreciable false positive rate. But there was a case where that happened, but it's just not possible to say if they truly were associated. So assuming that's not, then all we really have is just we have electromagnetic waves across the spectrum, but we don't have neutrinos or gravitational waves.
Question about the generation of neutrinos in formation of neutron stars and supernovas. My understanding is neutrinos are a sign of weak force activity. The transmutation of an up to a down always, involves a neutrino emission and so forth. So anytime something changes into something else, neutrinos are involved, be it in weak force. What's the cause, the mechanism of the generation of so many neutrinos in a supernova? Is it the transformation of all the protons in the various separate nuclei into neutrons, and then gluons holding this whole thing together, or what?
Yeah, I don't know the details of the sort of particle physics of it, to be honest. The reason for the very large numbers of them being produced in supernovae is really, I know that it has to do with the very, very high temperatures that you have. It's essentially the way that you cool down this newly formed neutron star, and basically the binding energy of this neutron star is released as neutrinos, but I don't know the details of the exact pathways by which you produce the neutrinos.
What is the progression from hydrogen to helium to the other element? What keeps it from going lockstep like that rather than saying, oh, I've got some two heliums, let's burn and carbon and move through the progression?
Right. So I couldn't hear super well. I think the question was, why does it go in such a specific order? Why hydrogen to helium, then helium to carbon? What stops you from having sort of other pathways of burning through these elements? Was that right?
Yeah, that's it.
Yeah, why a specific sequence? Right. So, you can sort of, people really understand the very specific chain reactions that happen. So, let's see, how do I say this? I guess you can kind of picture, to get from hydrogen to helium to carbon and so on, there are, oh, sorry, one second. Sorry about that. I just had to turn something off. So you can sort of picture, to get from one to the other, there are actually many, many, many different possibilities. So you're absolutely right. There are many different reactions that can get you there. But then you can actually calculate under certain physical conditions, some end up becoming much, much more likely to happen than others. And so basically, it's just because of the physical conditions that you have inside these cores, temperatures, densities, and so on. Certain pathways get favored much, much more than others. But actually, there are, they don't all go through the same one. It's something like, 70% this one, 20% this one, 10% this one, or 8% this one, and then 1% this one. So there are actually multiple chains that are taken. It's just that some are heavily favored in the specific physical conditions that you have, and you can sort of you can calculate those probabilities given those physical conditions.
I have a question while Greg is moving to another person. I was going to ask about the neutrino data, and well, you already answered that question. So my next question is, why aren't we seeing more neutrino data? And is there any effort to tune our neutrino detectors in ways to pick up more supernova neutrinos?
Right. I mean, we'd love to see more supernova neutrinos. The problem is a mismatch in sensitivity. So neutrino experiments, they're only really sensitive to they just can't, you're only really going to see a sort of burst of neutrinos if the supernova is super, super nearby, like essentially in the Milky Way or in the Magellan clouds or something like that. And just the odds that the supernova is going to be so close is just really low because the rate per galaxy is about once per century. And so we just haven't had a supernova nearby enough that we'd really expect to see that sort of burst of neutrinos. Now, you could still see an individual neutrino because neutrinos don't really stop. So it could come from very far away and we could still detect it. And so there are these sort of high energy neutrinos that have been detected by this neutrino facility called IceCube. And there's this whole debate about where they actually come from. Are they from certain kinds of supernovae? Are they from gamma ray bursts? Are they from AGN? But that becomes more of a statistical game of they just detect one, and then you try to cross match with other events that were found with other telescopes. And it's just very hard to prove an association. So the other way people try to do it is by what we call the background. So you also know the total amount of neutrinos arriving, and you can sort of model the source population that might produce this just overall sort of neutrino population or neutrino flux. And so people try to do that as well. But to really get something like with 1987A, this real sort of burst of neutrinos, that would only happen for a very, very nearby, once in a century type of event.
Supernova 1604?
Sorry, could you say that again?
Do you know the supernova 1604?
Do I know the supernova 1604? I don't think so.
Kepler.
Oh, Kepler. That's the Kepler one. Oh, then yeah, sure. Okay, I didn't know the year. Then yeah. I've not studied it, but
did it become a neutron star or a black hole?
Let's see, the Kepler one. What type of supernova was that? Wasn't that a type 1A supernova? There are a couple of these famous ones, like Kepler's supernova, Tycho's supernova, and people can actually figure out the type of supernova by taking a spectrum of the echo. So you can see the light echo of the supernova, and you can see what type of supernova it was. And I believe that Kepler supernova, I think that's a type 1A supernova, which means that it was the thermonuclear detonation of a white dwarf. So actually it's not the type of supernova that makes a neutron star or a black hole. I think, but I'm not 100% sure. I'm like 80% sure, I would say.
I was always curious about that because it shows the shell shock and it shows when the supernova, because the supernova was famous.
Yeah. I think I'm pretty sure that one was a 1A, but again, I'm just not I might be mixing up some of these. There are these really famous events where, someone saw the supernova hundreds of years ago. Today we see the supernova remnant, and then we can also get a spectrum of the light echo, which is amazing. So there's some of these beautifully well-studied events, and I just can't remember sort of which one is which, but definitely one of them is definitely a type 1a supernova. I think the Crab is thought, yeah, yes, I think that's right. I think the Kepler one is the 1a, in which case it would have been actually a white dwarf type of supernova, not one of these core collapse ones making a neutron star or a black hole.
I want to point out to the club more so than to you particularly, Anna. We have a negative from the Ocean Schmidt camera in the club.
Oh.
It's when they use glass plates. We have
okay.
taken from the camera that the Zwicky transient facility is now using.
Oh, okay.
Okay, if anybody in this organization wants to see what they used to come out with.
Yeah.
Okay, because it's a 14-inch square negative that is in focus from corner to corner.
Oh, wow.
Okay, when you take a look at the mechanics of the camera, it's a fascinating piece.
Yeah.
And the other thing is that we have two of them. One of them apparently was taken during an earthquake.
Oh, okay.
It's actually the notes page from Palomar.
Oh, wow.
Gutters and they close it right away. Okay, but just odd things that you got to deal with in California.
Yeah, I actually had an observing night. I was observing with the 200-inch telescope at Palomar to get spectra of supernovae discovered by the Samuel Ocean 48-inch telescope. And there was an earthquake while we were observing. And actually, the telescope operator felt it first, which was interesting. He said something like, oh, and I hadn't felt it yet. And then a few seconds after he reacted, suddenly the room started shaking. So we had to pause the observations. I think you feel these things also more on the tops of mountains. So it actually wasn't a very strong earthquake, but we definitely really felt it.
The other little bit of trivia is that you showed a cutaway diagram of the telescope. That's a rather famous diagram by a guy named Russell Porter.
Yep.
Who famously died before the telescope was built.
Right.
So all of the diagrams he did of the Palomar telescope are done from the drawings. There was no hardware.
Yeah.
The telescope was designed in the 30s, built in the late 40s, but something happened in the early 40s that kind of screwed everything else.
Yeah.
Yeah.
Yeah, my understanding is that his drawings were actually helpful in building the telescope, which is, I mean, pretty.
And see, for us, it's important because he is one of the founders of Stellafane, which is the home of amateur telescoping.
Oh, okay. Oh, I didn't know that.
And of course, 20 years before that, he was an Arctic explorer, spent his winters in the Arctic Circle. We think it's cold.
Yeah.
You guys were nuts. They started building Stellafane in December. Top of Vermont. Which one of us wants to go out and hammer nails?
Any more questions? Yeah.
Dr. Ho, have you ever been to Arecibo, or do you think it'll ever be built or rebuilt?
Oh, yeah, it's just such a sad story. Right. I mean, Arecibo has done such wonderful science for pulsars and for a lot else. I don't know what the future of Arecibo is going to be. I know it was already, some of these radio telescopes, the Green Bank Telescope, Arecibo, were already sort of, my understanding is sort of threatened by funding restrictions. And so I don't know that people are sort of particularly optimistic about it being rebuilt. I've heard people discuss sort of possibilities, but I've not, personally, I've not heard anyone really talk about it in a way that they really think it will happen. But maybe I'm just not in the know. I mean, it's really hard to, it's very, very difficult to get funding to build new telescopes. So yeah, it was really tragic.
I understand that the trend in radio telescopes these days is not to make huge antennas and steer it around, but to make these very cheap distributed antennas where there's maybe hundreds or thousands of them, and each one is very small. Like what they have in Australia and Africa and other places like that. Do you have any experience with those distributed radio telescopes, and do they have any disadvantages?
Yeah, so right. Let's see. There are trade-offs in the sense that, so one important number is the total amount of collecting area that you actually have. That sets kind of your sensitivities. That sets how faint of a thing can you see. The second thing is your number of kind of independent elements, because that kind of sets the resolution that you can get. So if you have two telescopes, suddenly you actually have two, you have a baseline, and you can actually start to say where this thing is coming from much better than you can if you just have a single dish. And so, yeah, so there are all these different types. And then there's the frequency, how big of a wavelength do you want to be able to detect? So if your thing is too small, the size of the wavelength you can kind of receive, you can sort of relate it to how big of a dish you actually have. So there are all these trade-offs, but one thing that has, one recent development is that it has become a lot cheaper to sort of mass manufacture large numbers of these smaller telescopes. And so there's a major project that I'm involved with to build a what's being called a radio camera, because they're going to have so many dishes. I actually can't even remember the final number. I could look it up if later if you're interested, but it's an enormous number of dishes, and manufacture some very large number of them, put them all over. It's sort of the core, I think, is going to be kind of Southern California. There's going to be some Owens Valley Radio Observatory, and then to expand them out and essentially have a giant radio telescope using a large number of these small ones. And so you get both the resolution and the sensitivity. And they're going to do a sky survey, so they're going to look for transients, which is why I'm involved. So that's called the DSA, DSA 2000. DSA stands for, I think, Deep Synoptic Array. So if you're curious, you could look that up and learn more about it. So that's definitely been a major development, but there's also a new, very large telescope, I think. What is the size of it actually? 400? I'm not sure. I can't quite remember, but a new one of those was just built fairly recently in China, and it was done to detect fast radio bursts, and it has been very successful. So I think it seems like both sorts of both sorts of avenues are still being pursued in modern astronomy.
Questions from online. Jackie did check, and Kepler was a 1A, as you said. So you were right on that. And it's been a pleasure having you speak to our group.
Yeah, thank you so much for attending. Feel free to reach out if you have other questions. And again, I'm sorry that I couldn't be there in person. And I hope you all have a great weekend.
You too. Thank you.
Thank you.